is and today we are going to learn about what is the electric field due to a non-conducting solid sphere. Okay, here we are going to assume a solid sphere of and that is uniformly charged with the volume charge density rho. Okay, so let us suppose that there is a solid sphere and it is uniformly charged with the positive charge. Let us say that it is uniformly charged and the total charge on this solid sphere is capital Q and the radius of this sphere is capital R. Okay, here the R is the radius of the solid sphere and capital Q is the charge which is uniformly distributed over the volume of this sphere. Okay, now we are going to find out that what is the electric field at a point which is outside the sphere and at a point which is inside the sphere, and one another case we are going to take in which we are going to take a point on the surface of the sphere, and we are going to see that what is the type of electric field or we can say how it depends on the distance from its center. So first case we are going to take is field outside the sphere. What will be the field outside the sphere? For that we are going to take a Gaussian surface of radius which is greater than the radius of the given sphere, that means r greater than r. We are going to take this case, and now we are going to assume a Gaussian spherical surface such that its radius is small r and that r is greater than the radius of the given solid sphere which is uniformly charged, and this charge Q is the charge of this solid sphere. Now first of all we should know that what is the charge enclosed by this outer shell which we have assumed. So here we have assumed the outer Gaussian surface which is the spherical surface. Now this outer Gaussian surface, it is enclosing the charge enclosed for this outer Gaussian surface will be the total charge which is we can say accumulated by the solid sphere. As we know that the outer part, because we know that the outer sphere which we are going to assume, that will have all the charge, whatever is the charge on the inner sphere, that will also be the part of this outer sphere. So that is why we can say that the charge enclosed by this we can say outer sphere is the charge on the sphere which was earlier. Fine. Now we are going to use the application of Gauss law here so that we can find out the electric field. Okay, one more thing here, what will be the direction of the electric field? Since we know that the electric field due to a positively charged particle, or we can say any positive charge, is always radially outward. Fine. So for the given solid sphere, it is positively charged, so the electric field will be pointing radially outward from each point. Okay, whatever distance we are going to take, this way or any other way, so the field will be along the radial we can say radius of the sphere, and it will be pointing outwards, radially outwards. So now using the Gauss law, we can write here according to Gauss law, the flux passing through this Gaussian surface, the flux passing through this outer Gaussian surface will be written as the closed integral over electric field dot ds vector equals to q enclosed by epsilon naught, where epsilon naught is the permittivity of free space and q enclosed with the charge enclosed by this assumed Gaussian surface. Now, as we know that the electric field is radially outward, the direction of the electric field is radially outward, and the direction of the area vector. Okay, here we are going to assume, let us say there is any area vector. Fine. So the direction of this area vector will also be radially outward. Let us say it is n cap. So the direction n cap is also radially outward, or we can say, as we know that the direction of the area vector due to a sphere is normal to the surface, or we can say it is radially outward. So we can say that the electric field and area vector for this particular case, they both have the similar direction. That is why the angle between the electric field and the area is 0 degree. So it can be written as E ds cos 0 degree equals to, what is the charge enclosed by this outer surface? It is capital Q and divided by epsilon naught. Okay. Now, as we know that the electric field is constant at each point. So that is why we can take this out of the integration, because it is constant at each point, because the distance is same and the electric field due to this positive charge will be same. So it will be E ds cos 0 is 1 equals to Q by epsilon naught. Now the surface area of this assumed Gaussian surface, it is, since it is the we can say spherical Gaussian surface of radius r, so it will be 4 pi r square. 4 pi r square and equivalent to Q by epsilon naught. And that is how we get the electric field outside the sphere. It is Q upon 4 pi epsilon naught r square. Q upon 4 pi epsilon naught r square. This is the electric field outside the solid sphere, which is non-conducting in the nature. And if you want to write it in the vector form, it can be written as E vector equals to Q upon 4 pi epsilon naught r square, and the direction is radially outside. This is the, we can say, the vectorial form of the electric field which we have found. And now you can see the dependency between electric field and the radius of the sphere which we have assumed, or we can say the distance of the point at which we want to find out the electric field due to this solid sphere. It is E proportional to r square. Sorry, E proportional to 1 by r square. The dependency between electric field and the point of interest is E proportional to 1 by r square, or we can say that electric field is inversely proportional to the square of the we can say the radius of the Gaussian surface which we have assumed. And the graph, if you want to draw the graph, so it will look like, on y-axis we are going to draw the electric field, and on x-axis, or we can say the horizontal axis, we are going to take the radius. So it will be like this. This is the type of graph which we get for the electric field outside the solid sphere. Now the another case which we are going to take, that will be the electric field at the surface of the sphere. What will be the electric field at the surface of the sphere? So for that time we can say that the Gaussian surface which we are going to assume, that will be having the radius equivalent to the radius of the sphere which was given. So we can write here field at R equals to R. So electric field will be E equals to, because the charge is same here, Q upon 4 pi epsilon of R square. This is the electric field at a point which we have taken at the surface of the solid sphere. Now the third case, we are going to take the electric field inside the sphere. What will be the electric field inside the sphere? For that we have to assume a Gaussian surface, the spherical Gaussian surface inside the solid sphere. Inside the solid sphere, and we are going to see in field inside, the third is the field inside the sphere, and here the radius of the Gaussian surface should be less than the radius of the given sphere. Okay, for that we have to assume a Gaussian surface such that it lies in the given sphere. So it should be like, let us assume a surface like this, and the radius of that assumed in we can say the inner sphere is R, and that R is less than R. Or if we remove this plus positive charge sign, so the diagram will look more, you can say, clear. So it will look like this way. This is the imaginary sphere which we are taking here this time, and the charge is Q, that is the total charge on this bigger sphere. Now our task is to find out what will be the charge enclosed in this smaller sphere